Okay, so welcome back, everybody. We stopped yesterday with pretty soon after our definition of adjacency matrix. So the first thing to note, right? So just recall that for graph G of order n, say vertices of G is the set we've labeled V1, V2, and so on out to Vn, right? The adjacency matrix A is the matrix. It's an n by n matrix with entries. So its ijth entries are, and again, this is the notation we're using just to be consistent with the textbook, even if it's a little cumbersome at first. So this is 1 if vertices Vi and Vj are adjacent, and 0 otherwise. Okay, so here's our adjacency matrix. Here's how we define this thing. Okay, now the first thing you might notice is I'm calling this the adjacency matrix, the matrix, right? Which might seem like I'm implying there is exactly one adjacency matrix for a graph, but notice that note. Well, what if I chose not even just say a different labeling of the vertices, that matters less here than this ordering that I'm putting on them. But remember that the vertices are not really ordered, right? They're just a set. So any ordering that I'm putting on them is coming like after the fact, and that could be changed and not substantively alter the actual like substance of the graph, right? So actually, if I had just ordered these vertices differently, the adjacency matrix obviously would be different, right? So like if I had, for instance, swapped the vertices I'm calling vertex 1 and vertex 2, that would swap the matrix. In fact, how would it swap the matrix, right? How is that going to be how's that going to be related? So note, if I had ordered the vertices of G differently, say instead of ordering them like this, I had V2 come first, and then V1, and then V7, and then V5, and so on in that fashion, right? Implying there's some fashion here. I didn't change the last vertex, right? So obviously the adjacency matrix that I get with respect to this is going to be different, right, than the adjacency matrix would change. It'd be a different matrix. Well, if it's going to be a different matrix, hopefully I would like to know there is like a very predictable, straightforward way in which this altered adjacency matrix is related to the original. And of course, let's just think about how that would work here. So how does this work? So how would the matrix change if I had altered these? What would be the change here? maybe we should think about it from the other side. All right, so say A and B are two adjacency matrices for the same graph G. So not even two isomorphic graphs, although we can think about what that means here in a second, but actually the same graph. It's just I have reordered the vertices. I have permuted the vertices, right? We're talking about what operation I performed on the vertices. They've been permuted from their original ordering here. So if I have two matrices that are different adjacency matrices of the same graph, what has to be true about A and B? Well, however, this permutation has been applied, going from the vertices corresponding to the adjacency matrix A and the permutation from that set of vertices applying to or giving rise to adjacency matrix B. That same permutation applied to the rows and columns of the matrix gets you B. So what must be true? Whatever permutation was applied to take the ordering of the vertices giving rise to A to produce the ordering of the vertices giving rise to B when applied to the corresponding rows and columns of A must produce B. So how are they related? What's a quick way of saying how they're related? Well, if there's a permutation taking you from the vertices that gave rise to the adjacency matrix A to vertices that gave rise to the adjacency matrix B, that same permutation applied to the rows and columns of the adjacency matrix A has to produce B. Okay, that's the relation. Okay, and this is basically just unpack the definition of adjacency matrix, and this is what you get. There's not much else to do here. This is essentially falling out of our definition of adjacency matrix. Okay, and the fact that permuting these vertices, of course, this is not in any way altering the connectivity of the graph. It's not altering the adjacency. It's not doing anything like that. This is literally just we are reordering what we are calling the first and second vertices, right? So and so on. So that's the point, and that's how these adjacency matrices must be related. So in fact, now if we think about this from another angle, right? This is important because we intuitively we thought of isomorphism of two graphs essentially being a relabeling, right? Well, a reordering is also a sort of relabeling. So I wonder if we can think of this as a way to determine in reverse whether or not two graphs are isomorphic. Well, let's just write that out. Note, the permutation mentioned here is, in fact, a one-to-one correspondence between the vertex set and itself. Since we know that isomorphic graphs have to have the cardinality of their vertex and edge sets have to be the same, we could ask the question, is every one-to-one correspondence between these finite sets like this essentially a permutation, right, when thought of in this way? And the answer is yes. Every one-to-one correspondence in this way exactly behaves in this manner. And so, what is the fact that we get out of this? Given two graphs, G1 and G2, having respective adjacency matrices A1 and A2, if one can apply permutation to the rows and columns of A1 to produce A2, so if we can apply a single permutation to the rows and columns of A1 to produce A2, then G1 and G2 are isomorphic. Oh, so this gives us a tool, potentially, for investigating this question of whether two graphs are isomorphic or not, using the adjacency matrices and whether or not we can, via permutation of the rows and columns of one of them, change it into the other. Okay, so that's nice. Now, I'm going to redo the example from yesterday, except I'm going to do slightly different. There's going to be one more edge in this example than the one from yesterday. So the graph from yesterday, I had this picture. And the way that the labeling of the vertices was starting here and going clockwise, V1, V2, V3, V4, V5, and V6. And I'm going to finish my connections here. So here, here, I think I was missing that edge yesterday. Here, and here. Okay. Think we're happy now. The adjacency matrix. 6 vertices, so of course it's a 6 by 6. Going row by row here, corresponding to the first row. Vertex 1 is adjacent to vertices 4 and 5 here, so 0, 0, 0, 1 in the 4th column, 1 in the 5th column, 0 in the 6th column. Okay, vertex 2 is only adjacent to vertex 3. Vertex 3 is adjacent to both vertex 2 and vertex 6. Vertex 4 is adjacent to 3 vertices, 1, 5, and 6. Vertex 5 is adjacent to 3 vertices, 1, 4, and 6. And lastly, vertex 6 is adjacent to 3 vertices, 3, 4, and 5. So there's our adjacency matrix for this graph. Okay. Now, because we did this at the end of the lecture last time, we didn't discuss too much more other than just, here it is. But you'll notice that thinking of the rows and columns, right? So for instance, the number of ones in, say, the first row corresponds to what? Right? This is the number, so the number of ones in the first row would be the degree of V1. Number of ones in the second row would be the degree of V2. Number of ones in the third row would be the degree of V3, and so on, right? So counting the number of ones here, say in a row or column, right, is counting degrees. Now, when I said that or column here, this is the fact that this is a symmetric matrix, right? So you might notice that I was saying, okay, the first row, that's telling me the adjacency of V1, but of course the first column is telling me that as well, right? The first column is also telling me that hey, okay, if this column is associated with V1 instead, right? If you're thinking of it like that, I have a 1 in the slot corresponding to V4 and a 1 in the slot corresponding to V5. So in the same fashion, this is how this goes. These are symmetric. I ask you to consider a situation in a graph. Maybe it's not simply just a finite simple graph, but on the first day of class we talked about a sort of graph where maybe the adjacency matrix wouldn't be symmetric. Maybe it makes sense for the adjacency matrix to not be symmetric, and you can ponder that on your own. But for us here, the finite simple graphs, we're not talking about digraphs or anything. These adjacency matrices are symmetric. So, okay. Here is this notion of like a count, for instance, of the ones in a row or column telling me the degree. What other things can I deduce from this matrix or from simple operations on this matrix? Okay. So here's the question. So note, I mentioned yesterday that a symmetric matrix with non-negative integer entries is really nice from a linear algebra standpoint. For instance, this tells you something really nice about its eigenvalues. We're in the simplest case here. It's diagonalizable. The eigenvalues are distinct. They're all real. So nice things here. Of course, eigenvalues related to very nicely dealing with, say, matrix powers, right? Raising a matrix to a power, iteratively multiplying a matrix by itself. So it's natural to say, okay, well, if that's the case and all that's nice, what can I say about iterative multiplication of this adjacency matrix? So A times A, for instance, right? A squared. Before I think about that, I want to note, we're just going to look at like an entry, we'll say. So note that the 1/6 entry in A is 0 because V1 and V6 are not adjacent. Okay. But what about the 1/6 entry of the matrix A times itself? Now, this is a 6 by 6 matrix, and yeah, it's filled with all zeros and ones, so it's not so bad. But, you know, matrix multiplying two 6 by 6 matrices, that might be slightly annoying. That's a lot of dot products, right? But if I'm just interested in a single entry, for instance, then this is just like a one single dot product, right? So this is the dot product of row 1 of A with column 6 of A, right? So the 1/6 entry, maybe I should use this notation here that we've been using. What is the 1/6 entry of the matrix A squared? This is the dot product of row 1 of A with column 6 of A, right? And so, what is that? We can write that out. That's not too bad. The row 1, of course, if we think about the column being transposed, right, we're not going to get into an argument over row versus column vector here. We know we have the vector set up in such a way you're dotting it with its transpose, whatever. We don't care. So I'm just going to write both of them as row vectors, even though one's a column vector that I've transposed, right? So don't fight me on that. So this is the vector 0, 0, 0, 1, 1, 0 dotted with the sixth column, which is 0, 0, 1, 1, 1, 0. Of course, this would be 0 squared plus 0 squared plus 0 times 1 plus 1 times 1 plus 1 times 1 plus 0 squared, which all these are 0 except these two entries, which are just 1, so this is 2. So not surprisingly, of course, when you multiply an adjacency matrix by itself, you get a matrix whose entries are not all just zeros and ones. That's fine. That's expected, right? You're dotting these things together. Of course, it's not just going to stay zeros and ones. But is there any significance to this number? So first of all, the 1/6 entry of A was 0, but the 1/6 entry of A squared was not 0. That is not too surprising necessarily, but let's think specifically for this example, since this is tethered to something very concrete here. Let's think about why this is. So what do we have here? We have, like, if we're looking in terms of the numbers, then the obvious answer, right, that's not going to satisfy anybody, right? This is the mathematician's answer. Why is this 2? Well, because there was a 1 here, right, that multiplied that 1, and there was a 1 here that multiplied that 1, instead of there being zeros in those slots. That's why it's a 2. Okay, well, clearly that's what's going on, but let's think a little bit more deeply about what that actually means, right? So there's a 1 in the first row corresponding to a 1 in the sixth column in the right place. Similarly, there was a 1 here in the first row corresponding to this 1 in the last column that, again, is in the right place. What does that correspond to? So there's the 1 in the fourth position of row 1 matched up with the 1 in the fourth position of column 6, right? So the 1 in row 1 matching up with this one matching up with this one represents what edge here? Well, it's the edge v1, v4, right? So maybe I'll even write that here. So this corresponds to the edge, this 1 corresponds to the edge v1, v4. And this one corresponds to the edge v4, v6. and this one corresponds to the edge v1, v5, while this one corresponds to the edge v5, v6. Okay. What is this? Do you see what it is that's going on here? I want to write this number as some words here. And does someone know what words I should use here about what is being counted? Well, this is the number of two-edge walks from v1 to v6. I wonder how this would have looked had you chosen some other vertices. So for instance, what about the 2/6 entry, right? The 2/6 entry of a squared. According to this, the 2/6 entry should be counting the number of two-edge walks from v2 to v6, of which there are exactly one. So the 2/6 entry of a squared should be 1. So you should check with yourself to verify that that is in fact the case. You could ask, is this a coincidence? Of course, the way that I've kind of painstakingly drawn this correspondence here, you'd think, well, no, this isn't going to be a coincidence. It didn't matter what slots we chose here. This was always going to work out in this fashion, right? And so we have the following theorem. So it turns out this is not an accident. This isn't part of the theorem statement, but wanted to stress that before I wrote the theorem statement. So let G be a graph with vertices v1 to vn, say. And let A be its corresponding, that is corresponding to this ordering, adjacency matrix. For any positive k, the ijth entry of the matrix power a to the k is equal to the number of walks from vi to vj that use exactly k edges. Okay. So proof. As you've no doubt guessed by this point in time, a lot of these theorems in early graph theory, and a lot of these theorems in graph theory, period, just based on the nature of the subject are going to be by induction. Induction's a powerful tool, not just when you don't know what's going on, it's just a powerful tool for something structured like this. So we prove this by induction. So first of all, base case, k equals 1. The result is true. Since the ijth entry of the adjacency matrix itself is equal to 1 exactly when there is a one-edge walk between Vi and Vj. This is just known as Vi and Vj being adjacent, right? So this is true exactly when there is a one-edge walk between Vi and Vj. We don't have to worry about the number here of one-edge walks because here we're dealing with a finite simple graph, so there's no other option, right? i.e. Vi and Vj are adjacent. Okay, so that's mostly true just by definition of the adjacency matrix. So now, suppose, this is the inductive step, so suppose for every I and j, the ijth entry of a to the k minus 1 is the number of walks from Vi to Vj that use exactly k minus 1 edges. Okay. Now, I, of course, want to prove this from this inductive hypothesis. I want to prove this for the kth object, right? I want to show that this is that the ijth entry of a to the k is the number of walks from Vi to Vj that use exactly k edges. So how do I do that? So first, I want to think about a k edge walk from Vi to Vj, right? So for any k edge walk from Vi to Vj, there is some, we'll call it h. So there exists some h such that the walk can be thought of as a k minus 1 edge walk from Vi to this V sub h. So there's some index here. There's some h such that the walk can be thought of as a k minus 1 edge walk from Vi to V sub h combined with the edge Vh to Vj. This is just our mathematically precise way of saying, well, any k-edge walk, you could just stop at the second to last stop, or your penultimate stop, right? So there's a choice of those. There's not necessarily just one of those. There's at least one, But there could be 5, 10, 15, right? There could be plenty of these. You just pick one of them, right? And we label that v sub h. So that's a k minus 1 edge walk, and then the last edge is your kth edge. Okay. But then what's the total number of these k edge walks? So the total number of k edge walks is going to be the sum over the vertices v sub h in the neighborhood. This is the open neighborhood, so it doesn't contain v sub j itself, of v sub j, of the number of k minus 1 edge walks from vi to vh. Right? Because, well, you have the last edge, right, taking you to vj. So all you have to do to get the total number of these k edge walks is just know the total number of these k minus 1 edge walks up until you're at the stop right before v sub j, right? This v sub h, wherever that is. So the total number of k minus 1 edge walks from vi to vh is the thing that counts this. Here, again, we're excluding v sub j. This is just all the vertices that are adjacent to v sub j, right? These are your potential second to last stops on a k edge walk, right? And we just chose one of them. Okay. But, of course, the thing is that by the induction hypothesis, the number of k minus 1 edge walks from vi to vh is just the ith entry of a to the k minus 1. So this is, we can rewrite this as the sum over these vertices v sub h in the open neighborhood of our vertex v sub j. This is the ith entry of a to the k minus 1. That's what all of this stuff is, right? By the inductive hypothesis. That's what we have done here. Okay. But, I mean, here, like, what is it that's actually going on here? How can we rewrite this sum in a way maybe more amenable to computation here? Well, if we are doing this sum over all possible choices of the vertices v sub h here, right, then how can I write this in a way that is going to produce what I want? So this may be a little bit confusing at first to see why these are equal, but I can rewrite this sum as the sum where h is from 1 to n of the ith entry of a to the k minus 1 times the hjth entry of a. But this is simply ijth entry of a to the k. And that's that. Okay. So we're done. We've proven what we needed to show, that this sums the total number of k edge walks. Again, you see that this is a result about counting, right? Again, telling us, hey, right, combinatorics is a fitting subject to pair with graph theory, because a lot of these results that we're interested in essentially come down to enumerative results, something where we are enumerating some set of things that we're interested in. Okay. So, state a quick corollary of this theorem. So this is very nice, right? Again, giving some more obvious power towards the adjacency matrix. So then, quick corollary of that theorem that we just proved. Let G be a graph with vertices labeled, we'll say V1 to Vn, as in the last. Let A be its corresponding adjacency matrix. Okay, in this course, if I use this abbreviation, I'm not talking about an adjoint matrix or an adjugate matrix. I'm talking about an adjacency matrix. So if I need to talk about those other things from linear algebra, I would write them out. So yeah, if I use this abbreviation, that's adjacency matrix. If the distance from, say, Vi to Vj is x, then the ijth entry of a to the k is 0 for k greater than or equal to 1, but strictly less than x. Proof, just think about the previous result. Previous result says that the ijth entry of a to the k is the total number of k edge walks from v sub I to v sub j. If the distance from v sub I to v sub j is x, meaning that x is the smallest number of edges needed to in a path from vi to vj, right? So this is the smallest number of edges needed. If that's x, then if k is strictly less than x, there does not exist a walk, a k-edge walk from v sub I to v sub j. Once k is equal to x, well, then this could be non-zero, right? But when k is strictly less than x, this has to be 0 necessarily, because x is the distance, which is the least number of edges connecting the two vertices, right, in a path. So that's what's going on there. And ultimately, of course, this result links with us the adjacency matrix and distances in matrix. So raising matrix to power gave us entries that told us something about distances, right? The number of k-edge walks from blah to blah. That's saying something about distances indirectly, as this corollary points out. And so here's the next idea in that vein. So going in that direction. So now let's see. Let us see if we can relate adjacency matrices further to distance, to our notion of distance. So what is the idea here? So again, we have graph G, order n, adjacency matrix A. If I just start writing G, N, and A, that's what I mean. So maybe I don't explicitly state these things, but unless otherwise specified, that's what I'm talking about here. Okay. So for positive integer k, define S sub k. We'll call this a matrix sum. Define this to be the n by n identity matrix I. All right, so this is the n by n identity. Plus a squared plus a cubed and so on up to a to the k. This might seem like it comes out of nowhere, but we're going to see very specifically what it is that's going on here and what the entries of this in this matrix sum are counting here, right? So the point is that the entries of I are ones and zeros, right? Here in I, the only ones are on the diagonal and zeros everywhere else. A, you have zeros on the diagonal, right? If we have no loops, and ones and zeros according to adjacency, right? Everywhere else. So since that is the case, then all of these, the entries of this S sub k are always going to be non-negative integers. So note, any entry of S sub k is a non-negative integer. And again, this is just because I and A only have ones and zeros. Okay, so there's nothing else that could happen here. Okay. Now, what this means is that if we consider this as a sequence, right, and seeing something written like this, your brain might already be like this has been beaten into you. You might look at this and say, oh, this is reminding me of some like sequence of partial sums sort of thing or something, right? So now I'm seeing the S sub k's as like a sequence of matrices here, and indeed they are. But because these are non-negative entries, each subsequent entry that I'm adding here is just adding more non-negative entries. So that is, greater than or equal to 0. Integers are being added, and so each successive matrix sum, right, consists of a matrix that entry by entry has larger entries, right? The entries are greater than or equal to all of the corresponding entries in S sub k. So way of saying that is that note that we have for every pair ij, the ijth entry of S sub k is less than or equal to the ijth entry of S sub k plus 1. So that's what you get from that. Now, what is this matrix sum S sub k telling us? Well, that is covered in the next theorem. So the next theorem sheds some light on this. What does the next theorem say? So theorem, Let G be a connected graph with vertices labeled in the usual way V1 to Vn. Let A be its corresponding adjacency matrix. Then, few facts. If K is the smallest positive integer, such that row J of S sub K contains no zeros, then the eccentricity of the vertex V sub J corresponding to that row is K. We're going to prove this. There's two more facts that I'm not going to prove. Your next homework, which I'll assign on Monday, will involve this. So we're only going to prove the first part here. Second part, if R is the smallest positive integer such that all entries of at least one row of S sub R are positive, that is not zero, then the radius of G is equal to R. And lastly, if M is the smallest positive integer such that all entries of S sub M are positive, then the diameter of G is equal to M. Now, just structurally, right off the bat, if I say, why do these have to be the smallest positive integer? Because clearly in this matrix sum, right, look at how the matrix sum is defined. In this matrix sum, you could just make K equal to 100 trillion, right? 100 trillion to the 100 trillion. Make it the biggest number you want to make it. And obviously, right, this is going to be eventually all positive. And the more you keep doing it, because every single entry, like all the entries divided in A are zeros and ones, every entry of these S sub K's are non-negative integers. So as you increase K, you're just adding more and more matrices that have more and more or strictly positive entries even, so that eventually all the entries are going to be positive, and then you keep adding non-negative integers to that. It's just going to be greater and greater, like all the entries are going to be greater and greater because of this fact, right? So that's why these need to be the smallest positive integers. Otherwise, this wouldn't make sense. This would not be well defined, because these facts, the row contains no zeros, that would be true, right? Like for K equals 5 billion, 50 billion, 50 trillion, right? That would be true, and it would be true for 50 trillion plus 1 as well. So that's why you have to pick out the smallest positive integer that does each of these things. Okay, so this very directly ties the eccentricity, radius, and diameter. All of those things, these things we use to define these concepts of distance, like the talking about the center and periphery of the graphs as we did. This ties very directly to both the adjacency matrix and this matrix sum that was defined in terms of the adjacency matrix. So I'm going to prove the first one. So proof of 1, 2, and 3 will be homework. So homework 2 will contain those. Okay, so suppose that k is the smallest positive integer. Suppose k is smallest positive integer such that row j of S sub k contains no zeros. Okay, so there's no zeros in row j. Okay, no zeros in row j of S sub k. So then what is the distance from v sub j to any other vertex? So what does this say? I'm going to bring S sub k back on the screen. Here it is. Recall from the previous theorem, bringing that back on the screen, that the entries of the ijth entry of a to the k is the number of walks from v sub I to v sub j that use exactly k edges. Okay. This corollary, of course, told us that if you have a distance between vertices vi and vj of x, then the entries of these a to the k are 0 for any k up to x, right? So consider that applied to this S sub k. If now we have a row, we've labeled as row j in S sub k, that contains no zeros. So here in this sum, there are no zeros in the row. Right? So every single entry is positive. That means that, remember, in S sub k, there's only this only goes up to a to the k here. It means necessarily, think of this corollary, right? That the distance from v sub j to any other vertex cannot be greater than k. Because if it was greater than k, all those corresponding entries, whatever that vertex might be, all those corresponding entries would be 0. Even in a to the k, they would be 0, which would yield a 0 entry in that row, right? So there would be a 0 entry in the row if that was the case. But since this row j contains no zeros, the distance from v sub j to any other vertex cannot be greater than k, right? So its distance to any other vertex cannot be greater than k. Okay. Of course, if k is equal to 1, the result follows immediately that the eccentricity then would have to be just one. Okay. What about k bigger than 1? K is bigger than 1. The fact that there's at least one 0 on row j of s sub k minus 1, because k is the smallest positive integer here, the fact that row j of s sub k minus 1 contains at least one 0. Again, if it did not, then k would not be the smallest positive integer such that row j of s sub k contains no zeros. K minus 1 would be the new candidate for smallest positive integer such that that's true. But, so it has to contain at least one 0 here. Okay, so there is at least one 0 on row j of s sub k minus 1. What does that mean? There's at least one vertex whose distance from v sub j is greater than k minus 1. I.e., there is at least one vertex whose distance from Vj is greater than k minus 1. But what is the definition of eccentricity? Right? This means that there's only one possibility for the eccentricity. It has to be k. So the eccentricity of V sub j has to be k. That's the only thing it can be. Recall how eccentricity was defined in the first place, right? So the eccentricity was the greatest distance from V to any other vertex. So your only option here, since the distance cannot exceed k, there's at least one vertex whose distance from Vj is greater than k minus 1. That means there's at least one vertex whose distance from Vj is k, but it can't exceed k. So k is the largest possible distance. That is, it is the eccentricity of Vj. Okay, so 2 and 3 you'll prove, like I said, as problems in homework 2. But that reasoning should get you started on how to think about those. So we can use adjacency matrices to create other types of graph-related matrices. So here is the idea, right? So here is an idea. Okay. So given a connected graph G of order n, adjacency matrix A, with S sub k defined as before. We just called it the matrix sum. Then we're going to create a matrix M. We'll call it M. Okay, so here is our process. For each I in the set 1 to n, let the ith entry of M be 0. Secondly, for each pair ij where I and j are distinct, let the ijth entry of M be k, where k is the least positive integer, such that the ijth entry of S sub k is non-zero. This is a big question. What exactly is the ijth entry of this matrix M? Do you see it? You see what it is that's going on here? Think about it for just a second. So we defined the ith entry. So if we're thinking about these entries being corresponding to vertex pairs, right? So the entry corresponding to vi and itself is 0. The entry corresponding to vi and a vertex vj is k, where k is the least positive integer, such that the ijth entry of sk is 0. Or sorry, is non-zero. What is the k where k is the least positive integer such that we talked about the least positive integer such that the row of sk had contained no zeros, or the row of sk all entries of at least one row were positive, or all entries period were positive. But what about just the least positive integer such that an individual entry is non-zero? What is that least positive integer? Well, the answer, this is just the distance from vi to vj. So the least positive integer such that the ijth entry of sk is non-zero, we have another name for that. That's called the distance between vi and vj. Okay. So that is what that is, and that is how all these things relate. Okay, so that's a decent amount of stuff to ponder. Now, you may be itching at this point, depending on your background or why you are interested in graph theory, why you're taking a graph theory course, you may be itching to apply some of these things to something, right? Depending. I don't know. Maybe you're just interested in graphs for their own sake. That's perfectly fine. That's a completely valid thing. But maybe you want to talk about how this applies to something else that you might be interested in more. And so, how about this notion of distance when used specifically for a situation where a graph is a model for something? So I'm not going to read all of these things. This is just a lot of reading. I'm going to say it in words. If you want something that might be easier to follow than just hearing me rant about it, then I would suggest you read, I'm going to say, pages 26 to, say 26 to get everything, 26 to 30. So this page is 26 to 30 in the textbook. What I'm going to talk about, though, are the acquaintance graph. Oh, misspelling everything here. Which relates to the notion of a Bacon number or an Erdős number. So what is the idea here, right? Uh, so an acquaintance graph, the canonical example, right, is you think of every single person in your life that you know. And when we use the word know, you can say, right, that this is basically anyone you've ever interacted with in person, online, maybe, right? If you maybe they're anonymous, you don't know exactly who they are, so we have to give them some label. You don't know their real name, you just give them some label, right? Like like cool guy 4792, right? That guy. You definitely know that guy. So however you want to define an acquaintance, right? You could make a graph, of course, where the adjacency relation, right? So adjacency relation uh, is going to be this notion of being acquainted. Now, of course, maybe some people are shut-ins. They're acquainted to like very few people, right? But they might happen to know the one, so these maybe are shut-ins, but they know this person that knows a lot of people, right? This person is a friend to shut-ins and non-shut-ins alike. Okay. So the idea here, right, is a graph is a perfectly fine model for this acquaintance network. And of course, you could think of doing this globally, right? So imagine you applied this globally, right? So how many vertices is that? Like 8 billion, right? 8 billion, little over 8 billion, I don't know, something like that. It used to be 7 billion 15, 20 years ago. Now it's 8 billion. Um, we'll say 8 billion plus vertices. Okay, so that's a lot of vertices. You might say, well, this seems impossible to have all of the data, all of the info be 100% accurate, and that's true. But nevertheless, this is something you could think about modeling this, right? And this is an absolutely massive data set. Computation trying to come up with this would be highly non-trivial. This is huge. You're going to have an adjacency matrix with 8 billion plus rows, right? I.e., A has 8 billion plus rows, which is fairly large for a matrix, I'm going to say, right? You might also have the problem that, of course, people are constantly being added, right? Babies are being born, people are dying. Of course, you could leave the dead connected to this graph, right? You knew the person that was once alive, right? That you can include that in the graph if you want to. So the point is that this is an absolutely gigantic data set, okay? Now, the idea is that something was noticed. As large as the vertex set is, seemingly the diameter is small. In fact, relating all of these things is this thing you've no doubt heard, or if you haven't heard, then I'm about to tell you, which is the 6 degrees of separation theory. What does this say? This basically says that the diameter of this graph is less than or equal to 6. Which is that even though this is absolutely gigantic, the idea being that there are no more than 6 degrees of separation between any human and any other human. Okay? So the idea here is, and of course, being an acquaintance could be taken very loosely. That's kind of part of how this is held together. Although, even not taking it entirely loosely, like there are some very, very good arguments for this being either true or mostly true. So one example that was done in 1967. So there was a 1967 experiment by Stanley Milgram. This is not the experiment you're thinking of. This is a different one. So the idea of this, or the experiment, was pretty interesting. So the idea was he randomly selected several hundred people from certain communities in the United States and sent a packet to each. Okay. Inside each packet was the name and address of a single target person. If the recipient knew this target personally, the recipient was to mail the packet directly to them. If the recipient did not know the target personally, the recipient was to send the packet to the person he or she thought had the best chance of knowing the target personally. Maybe they knew someone that was in the same state as the target, right? So it's like you have name and address of a target. You have no idea. You've never been to Utah, right? But you have a friend that went to college in Utah 20 years ago. So you mail the packet to that friend, something like that. So if the recipient did not know the target personally, the recipient was to send the packet to the person he or she thought had the best chance of knowing the target personally. The new recipient was to follow the same rules. Either send it directly to the target if they knew them, or send it to someone who has a good chance of knowing the target. So Milgram tracked how many steps it took for the packets to reach the target. Of the packets that eventually returned, the median number of steps was 5. Okay. So median number of steps was 5. Now you might fuss about some biases that might have crept into that, as far as you only track the packages that returned. Of course, how could you track a package if it didn't return? So all kinds of things that you could argue about here. But this led to the notion of small world phenomenon. What, of course, increases your the amazement that you feel when this happens to you, or when something you personally see happens to you in this way. This a lot of it is how loose and flexible the acquaintance relation is. It could be as simple as, I attended like a concert, right? And this other person was at the same concert as me, right? 20 years ago. And, maybe in a concert that has tens of thousands of people in it, that doesn't seem like it's that much acquainted. But of course, a single concert 20 years back, right? That is like maybe more of a special thing. There's all sorts of ways in which this happens, but you yourself have probably noticed something that has happened where you come across someone you never met before, and they end up knowing someone that you know in some random way, or being from or related to a place that you spent time in. There's all sorts of things that contribute to this. So this notion of small world, and I'm going to talk a little bit more about that. The notion of a Bacon number, or an Erdos number, is referring to, instead of acquaintance graph, this would be referring to the Hollywood. This would be a Hollywood graph where all of the actors that have worked in Hollywood are vertices, and the adjacency relation or edge relations between different vertices would be if they have starred in a movie together or been in a movie together, right? Maybe one was an extra in a movie, right? So Jackie Chan was an extra in Enter the Dragon with Bruce Lee. They never starred together, but Jackie Chan was like a guy that got his neck scruffed and thrown off screen in Enter the Dragon, so that counts. They were in the same movie together. So the distance between them will be 1. Okay, so Jackie Chan would have a Bruce Lee number of 1. But a bacon number is, this was originally popularized, focused on the actor Kevin Bacon, because he's been in a lot of movies, a lot of different people. So so this is why it's popularly known as the Bacon number, and people have computed various Bacon numbers for different actors and actresses. Erdős number, this would be like the mathematician graph. Again, Erdős was extremely prolific. He wrote like 1 billion mathematical papers, had so many collaborators. So if you had directly collaborated with Paul Erdős, you would have an Erdős number of 1. If you collaborated with a collaborator of Paul Erdős, you would have an Erdős number of 2, right? If that's your closest relation, and so on in that way. So, so all of these numbers, of course, are really computing distances, right? These are computing distances in these graphs being used to model these various situations. Okay, and so here's the thing, though. So in all of these cases, right? So in fact, there's even a there's a really funny project that I really enjoy. It's very funny. It's like the math genealogy project, which basically tracks like who was whose advisor, like who was whose PhD advisor for their PhD in math. So you can track your mathematical lineage going back to, and of course, because of some of these famous mathematicians had so many students, so most mathematicians active now can trace their math lineage like directly to either Euler or Gauss, or maybe even back to like Leibniz. So that's this is another sort of thing. It's a little bit different because of this. Actually, this math genealogy project ties into this is our next topic, which is going to be trees, or is more closely related to this versus these. Just thinking of a generic graph rather than a tree is what you're thinking of here. And these numbers are the distances, as I said. But what in all of these cases, what is essentially being noticed? What essentially is being noticed is this small world phenomenon. And the question is, what makes a small world small, right? Like, it's the amazement comes from the fact that you have a very large data set, a ton of vertices, but it seems like they're much closer than they should be, right? Should, again, being in quotes in your head, right? It's what is not meshing with your intuition is that it seems like things shouldn't be these vertices shouldn't be as closely related as they are. Okay, and so what is it exactly that makes a small world small? I'm going to just very briefly go over these things. It's fine if you're a little bit confused on these things. I just wanted to put these quantities down so that I can say what it is that's going on here. So the question is, what makes a small world small? And there are a few things. So that is what sorts of properties should these graphs have in order for it to have the same sort of small world feel of the acquaintance graph, like how you are connected to someone living in rural Egypt, right? Via a chain that is no longer than, say, 6 people, right? It's like, well, you are in this lecture being attended by, or being given by me. I went to Egypt like 18 years ago for a few months, and I met people in Egypt, right? Directly. Like, I stayed with some people in Egypt for a few weeks. So, what does that mean? That means you are connected through you being in lecture that I'm giving to someone in Egypt in this way, right? So, so that is the idea, right? Like that is how loose the connection can be, and that is how whether you know it or not, you have basically distance 2 from some person living in like Aswan, Egypt, right? Like almost like in a fairly remote place relatively. So um, anyway, and I don't even travel that much, right? So that's even more remarkable, right? it's, that's how it is. Okay, so then what is the idea here? So one, there should be plenty mutual acquaintances. So that's the big key here. You might see, like if you imagine an 8 billion vertex graph that's a giant cycle, that suddenly this is not a small world at all, right? If you're on the other side of the cycle from the person, you are very far removed from a vertex right on the opposite side. So like a cycle is about an empty graph, obviously, is everyone is completely isolated. So there should be plenty mutual acquaintances here, so shared neighbors. Now, you could say, hey, what about a complete graph, right? Complete graph, that's a lot of mutual acquaintances. Of course, that's true, but a complete graph is not a very accurate representation of, say, an acquaintance graph or how the world is related because, well, I mean, not everyone knows everyone on the planet, so and that's what would be suggested by a complete graph. The graph should be pretty sparse in edges relatively. So obviously not too much, but it should be sparse in edges. So relatively few edges compared to the number of vertices. So not so sparse in edges that the first thing is false, but relative to the number of vertices, there should be significantly less edges. Okay. All right. What next? Distances between pairs of vertices should be relatively small. Okay. So how do I know this? Here's an aside. How do I know this? For this, it is useful to discuss an an object or a quantity that is a little that is basically well suited for exactly this. So I'm going to define the characteristic path length of a graph G is the average distance between vertices. The average distance between vertices, where the average is taken over all pairs of distinct vertices. Of course, if two vertices are not adjacent, that distance um, um, is not going to be 1, right? Um, so here, what sort of thing am I doing here? So I have a graph of order n. We have distinct pairs of vertices, so graph G of order n has how many distinct pairs of vertices? It's the cardinality of the edge set of the complete graph on n vertices. But hey, your homework, right, from homework 1, which you haven't done yet, but it's assigned and you can do it. The cardinality of the edge set of the complete graph on n vertices is n times n minus 1 over 2. Oh, I wonder where that comes from, right? So, because this is the number of distinct pairs of vertices, and this is what you're averaging over, your characteristic path length, we'll call that L sub g. That is defined as follows. So L sub g is the sum over vertices u and v that are distinct vertices in the vertex set of G. I'm summing their distance, and I'm dividing that by the total number of such distinct pairs of vertices, which is cardinality of the edge set of the complete graph here. So this would be 2 over n times n minus 1 times the sum over distinct vertex pairs of these distances. This is just the average path length. So this is the average distance between vertices. Okay. So what's a way to do this, of course? Well, we defined this matrix M previously. What is the name of this matrix? Well, it seems fitting to call it the distance matrix for the graph. So this is the distance matrix for the graph. I can actually compute this by doing what? Just taking the average of the non-diagonal entries in the distance matrix. So take the average of the non-diagonal entries in the distance matrix for G. Okay. So this should be relatively small, this average path length. That's another thing that contributes to small worldness. Okay. What's the last thing that gives us small world properties? Okay. There should be a reasonable amount of clustering. In a small world graph. So how does this work? Well, in an actual acquaintance network, if we mapped out an acquaintance network for, say, residents of a state or country or even the whole thing, if we were to do this, there's plenty of factors, of course, that create clusters, right? So geography is one of them, right? You could consider like the clusters of people, in New York City versus, in like the middle of nowhere in Wyoming. So small groups of vertices among which there's a larger than typical portion of edges that exist, right? So people in New York City likely have more acquaintances in the loose sense than someone living in a cabin in Montana might. So you have these small groups of vertices among which larger than typical portion of edges exists. If I say take a vertex, so given, let's define what this clustering is, a vertex V in a graph order n. Define its clustering coefficient. So define its clustering coefficient. This is denoted as CC of V as the clustering coefficient. This is the cardinality of the edge set of the induced subgraph of the closed neighborhood of the vertex V. I know that is a lot of terminology there. Divided by the edge set of, so this is divided by, the cardinality of the edge set of the complete graph on 1 plus the degree of the vertex V vertices. But we know this, we know what this is, so this is 2 over n times n minus 1 here. So this would be 2 times the cardinality of the edge set of the induced subgraph of the closed neighborhood of the vertex V. That's a lot of parentheses, square brackets, corner brackets, and vertical lines over 1 plus the degree of the vertex times the degree of the vertex. Now you're going to be asking, okay, what the hell is this? Where does this come from? Where did this first proportion come from? So this is just us noticing that we know how to compute this number in general. So then, but where does this proportion come from? This is just the percentage of edges that exist among the vertices in a closed neighborhood of V. So this is the percentage of edges that exist among vertices in a closed neighborhood of V. So now that makes a lot more sense. When you put it that way, when you actually draw what this is, do this for a small graph, for instance, and you'll see what it is. So pick a graph of like 10 vertices or whatever. Don't make too many edges, and pick like a vertex that is decently clustered. So it has, say, we'll say like 4 or 5 edges, and you'll see what it is that's going on here, right? Okay. Now this is the clustering coefficient of a vertex. How do I measure the amount of clustering that the graph has, right? So there should be clustering of G. This is clustering of a single vertex. So what does clustering of G mean? So the clustering coefficient of G, so this is the clustering coefficient of a vertex. The clustering coefficient of G is then the average of the clustering coefficients. G is of order n. Is the average of the clustering coefficients of the vertices i.e., we'll write the clustering coefficient of G itself is, there's n vertices, so this is all over n, so this is 1 over n times the sum of all vertices in the vertex set of G, and I am summing their clustering coefficients. Okay, so this should be, there should be a decent amount of clustering. What you consider a decent amount of clustering, of course, is up to your particular applications that you're looking at. So, what is it that, like, why might you be interested in a small world network, right? So Something that satisfies all of these would be called, so 1 through 4 give us a small world network. Now, a small world network, you might say, well, I'm just interested in it because hey, that's like we can do this crude acquaintance graph of the entire planet, and it seems like that graph, right, if we could actually write down exactly that graph at any point in time, would be a small world network. So maybe that alone is a reason to be interested in it. But also, what sorts of things satisfy this? You might have already guessed. In fact, I already included it as kind of an example. But what also satisfies this? Well, the internet, power grids, neural networks. It turns out that there are many, many very concrete, very real world things that satisfy properties that turn it into what we could call a small world network. Going to mention one thing just because I put it in the video description. So rather than delete it from the video description, I'm going to mention it a single time. The next thing we're going to talk about are trees. What are trees? A tree is a connected graph. G that contains no cycles. We'll say this is acyclic many times. So for instance, this is a tree. This is not a tree. This contains that cycle. That would be enough to make it not a tree. It also contains this cycle. Okay. Next time, we will talk about the significance of this and why this is an important property to consider, and why a tree is an important type of graph to think about. Some of the special graphs that we've already mentioned are trees, and some are not. Right? So, for instance, a cycle is not a tree, but a path is. Okay, we will discuss all those things and more next time on Monday. On Monday, I will hang around a little bit after lecture in case you have some homework questions. You have, like I said, the whole weekend, and it's not due till Monday evening. So I'll always try to do something like that, essentially, by having some virtual office hours before a homework is due, so that I can help. I won't be like perfectly 100% helpful on purpose, but I will nudge you in the right direction for these things. So anyway, so if you have questions after working on the homework over the weekend, just tune in, like I said, a little bit after lecture. What I will do typically is I'll end the stream so that it's done and recorded, and then I'll start a new stream that's the office hours stream, and that'll be separate. So anyway, that is that. If you have any other questions over the weekend, just let me know, and I will see you all on Monday. Have a good weekend.